Look at this, a single grain of sand. Its size is about half a millimeter. It seems like the very definition of insignificant. Now let's begin a journey of scale. Imagine this tiny grain is our sun, the star that anchors our world and gives us life. On this scale, the Earth would be a microscopic speck of dust, about 15 centimeters away. Now imagine the beach this grain rests on. This beach isn't made of rock, it's made of stars. More than 200 billion of them, swirling in a colossal cosmic city that we call the Milky Way galaxy. If our sun is this grain of sand, the Milky Way would be a continent-sized beach stretching for thousands of kilometers. We are lost somewhere within it. But this beach, this continent of stars, is not the only one. For as far as our most powerful instruments can see, in every direction, there are other beaches, other galaxies. Modern estimates, powered by the James Webb Space Telescope, suggest there could be as many as 2 trillion of them in the observable universe. 2 trillion galaxies, each filled with hundreds of billions of their own stars, their own grains of sand. This is our universe. We live on a fragile planet, orbiting one unremarkable star in one of trillions of galaxies. From this minuscule peripheral vantage point, how did we ever figure this out? How did a species that once believed the stars were just lights fixed to a celestial ceiling come to map the infinite and read the history of creation itself? This is not just a story of science. It's the story of the greatest intellectual journey humanity has ever taken. The story of how we shattered our cosmic walls, tamed infinity, and unveiled the true nature of reality. For over 1,500 years, the Western world embraced a universe that was elegant, orderly, and deeply reassuring. Based on the ideas of Aristotle and mathematically refined by Claudius Ptolemy in the 2nd century AD, this was a cosmos built for us. Earth was stationary and central. Around it, the celestial bodies moved in perfect circles, embedded in crystalline spheres. The stars were eternal, unchanging lights fixed to the outermost sphere, a great wall that enclosed reality. It was finite, hierarchical, and knowable. It was a divine machine, and we were its purpose. This Ptolemaic model was a masterpiece of ingenuity. It could predict the positions of planets with remarkable accuracy. It aligned perfectly with philosophical and theological doctrines. It was, for all intents and purposes, the settled science for 50 generations. To question it was not just to question astronomy, but to question the very fabric of society, philosophy, and faith. The first major cracks appeared with Copernicus, who dared to place the sun at the center of the planets, but even he kept the stars fixed to a distant sphere. It was an English astronomer, Thomas Digges, who took the truly terrifying leap. In 1576, he translated Copernicus's work, but added his own radical illustration. He shattered the celestial sphere, scattering the stars into the infinite depths of space. He proposed they were just like our sun, stretching on forever. This was a terrifying, exhilarating idea. If the universe was infinite, it had no center. It had no edge. Where then was God's throne? Where did humanity fit into this boundless, indifferent cosmos? The comfort of the ancient walls was replaced by the terror of the infinite. And this new infinity brought with it profound and baffling paradoxes. The first paradox was one of gravity. Isaac Newton, the architect of our understanding of gravity, realized that an infinite universe posed a serious problem. If the universe was infinite and uniformly filled with infinite stars, then every single star should be pulled in every direction by an infinite number of other stars. The net gravitational force everywhere should be infinite, and the cosmos should have collapsed into a single monstrous clump. Why didn't it? The second, more famous paradox was one of light, later articulated by the German astronomer Heinrich Olbers. The paradox is this: if the universe is infinite in extent, has existed forever, and is filled with stars, then no matter where you look in the night sky, your line of sight should eventually end on the surface of a star. There should be no dark patches. The entire canopy of the night sky should be as bright and hot as the surface of the sun. Our world should be incinerated. So the simple, observable fact that the night sky is dark becomes a profound cosmic clue. It tells us that one or more of the core assumptions, infinite size, infinite age, static nature, must be wrong. This simple question, why is it dark at night, would haunt scientists for centuries. To answer it, and to answer Newton's paradox, would require us to completely rethink space, time, and gravity. But first, we needed a better map. We needed to measure the first rung on the cosmic ladder. The first reliable method for measuring the distance to stars is called parallax. The principle is simple. As the Earth orbits the Sun, our vantage point shifts by about 300 million kilometers. This causes nearby stars to appear to shift their position slightly against the backdrop of more distant stars. By measuring the tiny angle of this apparent shift and knowing the diameter of Earth's orbit, we can use simple trigonometry to calculate the star's distance. The smaller the shift, the farther away the star. For centuries, astronomers tried to detect this shift, but failed. The stars were simply too far away, the angles too minuscule to be measured with their instruments. This failure was even used as an argument against the sun-centered model. Finally, in 1838, the German astronomer Friedrich Bessel succeeded. He measured the parallax of the star 61 Cygni, calculating its distance to be about 11 light-years. It was a landmark achievement. For the first time, we had a concrete sense of the immense void separating the stars. But parallax only worked for our closest neighbors. For the vast majority of stars, and for the mysterious fuzzy patches called nebulae, the shift was too small to detect. To go deeper, we needed bigger eyes and a revolutionary new yardstick. The next great leap came not from an established academic, but from a German-born musician and composer who had moved to England, William Herschel. Obsessed with astronomy, Herschel was frustrated by the poor quality of existing telescopes. So, with the indispensable help of his sister, Caroline, he decided to build his own. And he built monsters. These weren't just telescopes, they were light buckets. Their enormous metal mirrors could collect light from objects fainter and farther away than anyone had ever seen. William was the observer, the visionary. Caroline was the mathematician, the recorder, and a brilliant astronomer in her own right, discovering several comets and updating the official British star catalogue with hundreds of previously unlisted stars. Together, they formed one of the most productive partnerships in scientific history. For decades, they engaged in a monumental project of stargazing, systematically counting stars in different regions of the sky. Their goal was to deduce the shape of our star system, the Milky Way. Their resulting map, a flattened, irregular disk of stars, was the first ever attempt to chart the galaxy based on empirical evidence. It incorrectly placed our sun near the center, but it correctly revealed the basic flattened structure of our home. But their powerful telescopes revealed a deeper mystery. The sky was littered with faint, fuzzy clouds of light they called nebulae. Some seemed to be churning clouds of gas, true nebulas where stars were being born, but others seemed different. They were faint, spiral-shaped smudges. What were they? Were they gas clouds inside our Milky Way, or were they something else entirely? Could they be, as the philosopher Immanuel Kant had speculated, island universes, entire galaxies just like our own, but so mind-bogglingly far away they appeared as faint smudges? The mystery of the nebulae would ignite one of the most famous disputes in astronomy, the Great Debate. In 1920, two prominent astronomers, Harlow Shapley and Heber Curtis, met in Washington, D.C. to publicly debate the scale of the universe. Shapley, on one side, argued that the Milky Way was the entire universe. He had done groundbreaking work mapping the galaxy's true size, far larger than anyone thought, and correctly placed the Sun in its outer suburbs. He believed the spiral nebulae were simply gas clouds within our own enormous galaxy. Curtis, on the other hand, was the champion of the island universe hypothesis. His evidence was observational. The spiral nebulae looked just like our own galaxy, and he pointed to the discovery of novae, exploding stars in Andromeda that suggested it was incredibly distant. The debate was a stalemate. Both men had valid points, but both lacked the definitive piece of evidence, a reliable measurement of the distance to the nebulae. The key to settling the debate lay in a new technique, spectroscopy. By passing starlight through a prism, astronomers can see its spectrum, a rainbow of colors with dark lines cutting through it. These lines are like a chemical barcode, revealing exactly which elements are present in the star's atmosphere. In the years leading up to the debate, an astronomer at Lowell Observatory named Vesto Slipher had been painstakingly measuring the spectra of the spiral nebulae. He found something astonishing. The spectral lines of nearly all of them were dramatically shifted towards the red end of the spectrum. That key was forged in the quiet, meticulous work of Henrietta Leavitt. As a computer at Harvard, she was tasked with the repetitive work of analyzing photographic plates. Leavitt, who was deaf and received little professional recognition in her lifetime, was studying a special class of stars called Cepheid variables. These stars rhythmically brighten and dim. Leavitt's genius was to notice a direct, unshakable relationship. The faster a Cepheid pulsed, the dimmer its true brightness. The slower it pulsed, the brighter its true brightness. This period luminosity relationship was the cosmic yardstick everyone had been searching for. If you could find a Cepheid, you could measure its pulse period. From that, you knew its true wattage. By comparing its true wattage to how dim it appeared from Earth, you could calculate its distance. It was a discovery of monumental importance, one that would allow us to measure the universe itself. The man to wield this key was Edwin Hubble. A former lawyer and amateur boxer, Hubble was a force of nature. In the early 1920s, using the colossal 100-inch Hooker telescope on Mount Wilson, he began a systematic hunt for Cepheids in the largest and most controversial nebula, Andromeda. Night after laborious night, he took photographic plates of Andromeda's faint, swirling arms. And then, in October 1923, he found one. He compared his plates and saw a tiny pinprick of light that was changing in brightness. He excitedly circled it, writing VAR for variable. He measured its period. He applied Leavitt's law to find its true brightness. And then he did the calculation. The result was world-changing. The Cepheid in Andromeda was roughly 900,000 light-years away, 3 times the size of even Shapley's most generous estimate for the entire Milky Way. The great debate was over. Andromeda was not a gas cloud. It was a galaxy. A vast, majestic island universe containing hundreds of billions of stars. And if Andromeda was a galaxy, then so were the thousands of other spiral nebulae. Hubble then combined his distance measurements with Vesto Slipher's redshift data. The pattern was undeniable. The farther away a galaxy was, the faster it was receding from us. This became known as Hubble's law. The conclusion was inescapable. The universe itself is expanding. Every galaxy is moving away from every other galaxy because the very fabric of space is stretching. This discovery finally solved Olbers Paradox. The night sky is dark because the universe had a beginning, and the light from the most distant galaxies is stretched into lower and lower energies as it travels through an expanding space. Running the clock backward, this expansion implied that everything in the cosmos must have originated from a single, hot, dense point. An idea that would later be mockingly dubbed the Big Bang. But why was the universe expanding? Why wasn't Newton's gravity, which so perfectly described the fall of an apple and the orbit of the moon, pulling it all back together into a great collapse? The answer had been published in 1915, before Hubble's discovery. But its cosmic implications were not yet understood. It came from the mind of Albert Einstein. Einstein's general theory of relativity was a complete demolition of Newton's concept of gravity. He proposed that gravity is not a force, it is a consequence of the geometry of the universe. Mass and energy, he said, warp the 4-dimensional fabric of space-time. And this curvature of space-time, in turn, dictates how objects move. A planet orbiting the sun isn't being pulled by an invisible rope, it's simply following the straightest possible path, a geodesic, through the curved space-time created by the sun's mass. This new theory made a stunning prediction. Not just matter, but light itself should follow these curves. An opportunity to test this came during a total solar eclipse in 1919. An expedition led by English astronomer Arthur Eddington photographed the stars near the eclipsed sun. They found that the starlight was indeed bent by the sun's gravity, precisely as Einstein's theory predicted. The discovery made Einstein a global celebrity overnight. But when Einstein applied his equations to the universe as a whole, he found they predicted that the universe could not be static. It must either be expanding or contracting. Believing the universe was eternal and unchanging, Einstein couldn't accept this. He introduced a fudge factor into his equations, the cosmological constant, to force a static solution. When Hubble announced his discovery of the expanding universe years later, Einstein visited him at Mount Wilson, looked through the telescope, and conceded. He later called the cosmological constant his biggest blunder. His own theory had predicted the expanding universe, but he hadn't had the audacity to believe it. By the mid-20th century, the Big Bang model, born from general relativity and confirmed by the expansion of the universe, was the leading theory. It was further solidified in 1965 by the accidental discovery of the cosmic microwave background, the faint leftover heat from the Big Bang, a fossil echo of creation. But as our observations improved, new cracks began to appear in our understanding. The universe was more mysterious than we knew. In the 1970s, an astronomer named Vera Rubin was studying the rotation of galaxies. She expected to find that stars on the outer edges would move more slowly than stars near the center, just as outer planets in our solar system move more slowly than inner ones. But that's not what she found. The outer stars were moving just as fast as the inner ones. The only way this was possible was if the galaxies were filled with a huge amount of invisible, undetectable mass whose gravity was holding these fast-moving stars in orbit. She called it dark matter. Her findings were dismissed for years, but the evidence became overwhelming. We now believe that for every 1 gram of normal matter, stars, planets, us, there are 5 grams of this mysterious dark matter. It forms a vast invisible scaffold upon which the cosmic web is built. We know it's there by its gravitational effects, but we have absolutely no idea what it is. Then, in the late 1990s, came an even bigger shock. 2 teams of astronomers studying distant exploding stars, supernovae, were trying to measure the rate at which the universe's expansion was slowing down due to gravity. They found the exact opposite. The expansion wasn't slowing down at all. It was accelerating. Something was actively pushing the universe apart, acting like a cosmic anti-gravity. This mysterious influence was dubbed dark energy. It turns out Einstein's biggest blunder, the cosmological constant, might not have been a blunder after all. It may be the best description we have for this dark energy that seems to be a property of space itself. Today, our cosmic inventory is humbling. About 70% of the universe is dark energy. 25% is dark matter, and a mere 5% is the normal matter that makes up everything we have ever seen or touched. This discovery points towards a strange and lonely cosmic future. As the dark energy-fueled expansion continues to accelerate, galaxies will be pushed away from us faster and faster. Eventually, one by one, they will cross a cosmic horizon, receding from us faster than the speed of light. Their light will never be able to reach us again. The cosmic beaches will vanish over the horizon. Future astronomers in our galaxy will look out into a great empty darkness, with no empirical evidence that other galaxies ever existed. The grand cosmic story, which we worked so hard to read, will be erased from the sky. They will be trapped once more behind a wall, not of ignorance, but of the fundamental nature of space-time itself. From a tiny world of rock and water, we have looked out into the darkness and seen back to the dawn of time. We have pieced together a story of unimaginable scale, from the subatomic to the cosmic, from the first second of the Big Bang to a future of accelerating emptiness. We learned our true place, not as the centerpiece of a tidy creation, but as a temporary consciousness on a grain of sand in a vast, dynamic, and deeply mysterious ocean. We have replaced the comforting certainties of our ancestors with a profound and perhaps more beautiful uncertainty. We may never know all the answers, but the fact that we can even ask the questions is perhaps the most wondrous thing in the universe.